Good afternoon, everyone. Welcome to Rediscovering the Space, our cycle of inspiring speeches for the PhD program in Aerospace, Science and Engineering at Politecnico di Bari. As you know, we decided to organize these events with the aim of inspiring and excite the interest of PhD students on different aspects of the aerospace field, regardless of the theme of their research projects. We tried to tackle very different topics, from space architecture to space economy, passing through space telescopes and Martian rovers, to name a few. So indeed, so far, it has been a very good opportunity to learn new things and to exchange ideas on multidisciplinary teams. Today, I'm very pleased to host an exceptional guest, Roberto Battiston, Professor of Experimental Physics at the University of Trento, who will talk about the limits and perspectives of space exploration. I welcome Professor Battiston, and I really want to thank him for his time and for sharing with us his vast experience. I leave the floor to Vito Albino, Professor of Business and Management Engineering at Politecnico di Bari, who will introduce the speaker and moderate the event. Thanks for participating.
Thanks, Professor De Tullio. Thanks for the invitation to be a moderator of one of the inspiring speeches in the PhD program of Aerospace Science Engineering. I really appreciate this initiative of Politecnico of Bari and the University of Bari, because I think that young students, young PhD students at the beginning of their professional career should fall in love with ideas and projects. And our duty is to offer them opportunities to fall in love. Today, as you said, Marco, we have a very special guest speaker with us, and have the great pleasure to moderate this event. Professor Battiston is a professor of physics at University of Trento, and my duty today is very simple, because Professor Battiston is very well known in the scientific community of aerospace, as well as to the general public for his role in very important organizations. I have to say now that he's becoming very famous also for his reliable analysis of data related to COVID pandemic. So anyway, I have to say also that for this duty, I feel it a bit hard to do this duty, because presenting Professor Battiston, I have to make a selection in his outstanding curriculum. But as usual, I will say something about the career of Professor Battiston. He graduated in physics at Scuola Normale di Pisa and received a doctorate at the University of Paris, Neuf, in 1982. Now he's professor at the University of Trento. For almost 40 years, he has been involved in international research projects in the field of experimental physics and fundamental interactions. In particular, he did research on antimatter and dark matter in cosmic rays. He has coordinated very important scientific projects in the field of accelerator physics at CERN, at Stanford, and in the space. In particular, together with Nobel laureate Professor Ting of MIT and CERN, he proposed and coordinated the implementation of an experiment for search for antimatter, and the alpha magnetic spectrometer has been installed on the International Space Station. He has also been active transferring the results and technology of basic research into the advanced applications in very different fields. From 2014 to 2018, he was the president of the Italian Space Agency, representing Italy in European and international space contexts. Professor Battiston has been committed to the dissemination and use of scientific space data for the development of society. in particular, I wish to remember that he contributes to the approval of the National Space Economy Plan based on a public-private partnership model, and he proposed and supported the development of the first Italian public-private investment fund for space. He has given invited talks everywhere in the world. He regularly writes for newspapers like Repubblica and Corriere della Sera. But what I like to underline of Roberto Battiston is that he is an all-round professor and researcher. Research, teaching, dissemination, public engagement. Well, the title of the talk today is Space Explorations, Limits and Perspectives. Let me say a few words about the topic, just as a quick introduction. As we know, in the history, all explorations have been great challenges for humanity. Usually, we remember the name of the people that did the exploration. But in all exploration adventures, the role of technology has been fundamental. Technology often has been an enabler of the exploration. This is true also for space exploration. The actual problem of space exploration calls for new technologies, and some limits have to be overcome. The colonization of the moon, and then the big challenge of colonizing Mars. But which technology would space exploration need, and we don't have yet? Today, Professor Battiston will drive us in the discovery of the frontier of space and technology. Roberto, please, the floor is yours. And thank you again to stay with us today.
Do you hear me? Do you
Yes.
hear me? Okay. Thank you. Thank you very much, Vito. It's really a pleasure to be introduced by a colleague which has has devoted so much time to space application and space economy, and which can really evaluate and introduce to students various aspects of this beautiful adventure, which is space. Today, considering that I'm talking to students which are both interested to technology as well to science, which are interested to space, I tried to talk about space, taking into account not only what we as humanity did, but also, and most important, what we want to do, what we want to achieve, and give some ideas, some visionary ideas about what we should do in order to make the next steps into the space adventure in exploring space. We live on planet Earth, a small blue dot, pale blue dot, as Carl Sagan was describing Earth in one of his beautiful books, in the solar system, which is one of the many star systems in our galaxy, which is one of many galaxies in our universe. So we are on a small corner of something which is extremely vast. And in spite of the great discoveries and exploration we did around the Earth, to the moon, landing on Mars, exploring the solar system, we have to acknowledge that what we are doing so far is just a little bit of a potential which is really infinite. Okay, now, the adventure started in October 4th, 1957, when the Soviet launched Sputnik, the first artificial satellite into the orbit around the Earth. It was a total revolution, was totally unexpected. It took the American by surprise and started what we call today the space race. To make the story very short, on April 12, 1961, the Russian, Soviet Union indeed, was still very much in advance to the United States. Yuri Gagarin was launched to space aboard the Soviet vessel Vostok 1, the first human to orbit around Earth. But to make the story very, very short, 8 years later, on July 20, 1969, Neil Armstrong and Buzz Aldrin became the first men to reach the moon. And this basically defined the kind of end of the space race, because after this competition, the space has evolved, but the competition was totally different, and it became also collaboration. It's important to recall that, because today the situation is getting back a little bit as in the early days. Just yesterday, Russia and China have announced that will join forces to organize a colony on the moon, calling international participation to that. Exactly the same American and European are doing on the similar project. Just to say that a new space race may be ongoing right now, but I mean, let's see what is going on, but keep in eyes, because things are going to become very interesting on that. Okay, the space race, the standard space, the historical space race, started in the 60s and they lasted about 15, 18 years. But the man on the moon was the most important achievement, which certified the potential, the capacity of the Americans in exploration, in space exploration. Keep in mind that Russia never made a man to the moon. Russia never made a satellite landing on Mars. So, I mean, aside of an extremely successful start, at a certain moment with the Apollo program, the American system was able to get to much more ambitious goal than the Soviet Union one. Today, space is much, much more than a space race to put a flag on a satellite or another planet. Space is about observing Earth. Space is about telecommunication. It's about navigation with the GPS, with the Galileo. Your cell phone are equipped with space capability, and this is what is guiding you through traffic. Space can observe small changes on the Earth's surface. This photograph is an interferometer using a radar satellite system by ASI, the Italian Space Agency, capable to see the movement of the Vesuvio volcano and the area of Napoli, monitoring of the potential risks of a forthcoming eruption. So this is what space can do today. This is just one example of many which are possible. Space is changing nowadays. It's changing because so many things are happening in the last 20 years. This photograph is showing that from the space station, the International Space Station, we will mention briefly that it is possible to launch nanosatellite using a very simple spring-loaded system. And those small satellites can make constellation of hundreds of those. And Planet.com is a company founded by 7 engineers, young engineers, about 10 years ago, which was able to develop those small satellites, the first sophisticated nano satellite, able to take picture of the Earth every day, every single square meter. And those satellites are cheap and inexpensive and can be developed in a very short amount of time. Space is changing quickly also because getting to space, access to space, is being revolutionized by the SpaceX, developing launchers which can return to Earth and land safely to be reused several times. This was not possible 6 or 7 years ago. It became suddenly possible in 2015, in the Christmas period of 2015, when SpaceX landed for the first time the first stage of the Falcon X. And this as a consequence of decreasing cost and improving the accessibility to space. So today, however, I will not discuss about what is space today. I mean, space economy, the cost and prices which go down, access for smaller companies, all of that, space economy. I will not talk about that, which is a fascinating topic. But I will now look farther away in the far future to understand which will be the future in 20, 30, 40 years from now, and taking space exploration as the topic to answer this question. This picture that you see here now is a NASA sketch, which try to explain in one single picture what implies going from where we are now to a colony or a presence of mankind on Mars. Today we are orbiting around the Earth. We have the space station. We learn to live on the space station on space for up to a year, to operate there in microgravity, to develop all kinds of systems and technologies. We have the capability to put in space all kinds of satellites close to the Earth, to go to the moon, and there is a new program to go to the moon with Orion and other launchers. You have heard that SpaceX has been selected for that, to make a human-based, but we are also able to go to asteroids, to go to Mars with landers. You have just heard the recent achievement of Ingenuity, the helicopter on Mars. So all of those developments, you have to look at it in a coherent fashion, because each of those developments are bringing in something which will be needed for the most audacious, most difficult operation, bring men on Mars, bring a colony on Mars. Because Mars is far away. It's not like the moon. You can be reached in a few days of travel. And in case of an issue like Apollo 13, you can even bring back, if you, with some luck, people back, the astronaut back to the Earth, even in a very difficult situation. Mars is totally different. It takes 6 months to go there. You have to wait there for a few months, and another 6 months to come back. Nothing can go wrong. If things go wrong, there is no hope to save the people so far away. If you remember Il Sopravvissuto, the Martians, these astronauts had to survive by himself because from Earth, nothing could be done before several months, and nothing was designed to give food to these astronauts for so long time. So let's now discuss and try to see what would imply if we're really serious to go to Mars. And let's get into that step by step, making some consideration about what we are able to do today and what we are not able to do today. First of all, if you get to this space, radiation is an issue. I will show you why it's an issue. The sun is erupting with certain frequency, burst of energetic particles, ionizing particles, X-rays and gamma rays. This is typically connected to the sunspot activity. Sunspot can be very small compared to the sun, the size of the Earth, but can be very dangerous because they emit so much material, mass ejection of particles at high energy, getting to the Earth after a few days and being deflected away by the Earth magnetic field. Then in the north, you see the Aurora Borealis are due to this kind of phenomena. The Earth is protecting ourselves, but in certain regions, like the poles, the Aurora Borealis are telling us that something is going on out there. So on Earth, we are protected by magnetic field, by the atmosphere, by the shadow of the planet. But what would happen if something like that happened while we are traveling to Mars, in the 6 months of travel to Mars? Without protection, the astronaut would be really in trouble in case of such an event would happen. So this is just an example. This is just an example. We come back on that because we are not, as human species, designed to stand high doses of radiation. We are used to live on Earth, protected by atmosphere, magnetic field, and the planet itself. However, of course, we have been very brave, and in the last 20 years, we built the International Space Station, which is operating there since more than 20 years now. So if you have in your 20s or your friends in the 20s, not a single day, somebody which was born at the beginning of this century, the space station was not operated by an astronaut or more astronauts living there. The International Space Station is just beautiful. This is a photograph taken by a shuttle which was approaching the station when the shuttle was still operating. And you can see it's full of cylinders, which where the laboratories and the living quarters are. There is the Russian segment, this part here, the American and European segment, this part here. This is an experiment looking for cosmic ray, the alpha magnetic spectrometer, where Luca Parmitano did incredible EVA, extravehicular activity, last year. These are the panels, these are the radiator. It's just an incredible 5-star hotel in sky. However, even this beautiful achievement, the larger, most complex, expensive technological achievement of mankind ever, could have and had some problem. And this happened again to Luca Parmitano, not last year, but several years ago. It was doing an EVA. And while doing an EVA on the outside of the space station, he realized that was some anomalous amount of water floating around him, attaching to his head, covering his eyes, entering in his nose, his mouth. The mic get off for short circuit, as well as the loudspeaker. And what was going on? Initially, he thought he was sweating, but it was not. What happened, I can tell you, because it was understood in detail. On the back of this helmet, there is a valve. And this valve is controlling the fluid which keep the astronaut refreshed in the suit, because the suit can be exposed to the sun or can be exposed to the very cold deep space. So these liquids are kind of averaging the temperature and keeping comfortable for the astronaut. So this water was leaking out, and in space, the water float and make bubbles, big drops, big bubbles of water, which was attaching to the surface because of surface tension. To make the story short, in a few minutes, Luca was unable to breathe anymore, was unable to talk, could not clean his face with his hand, because the hands were trapped in the suit, and was really confused what was going on. Was brave enough to go back to the cabin, where he could increase the pressure again and take away the helmet and the suit. But it was extremely dangerous what happened. Literally, it was at a risk to be drowning in half a glass of water in space. If I assume it seems like a joke, it was very serious, because what happened, nobody realized the danger of this particular detail breaking down in an unexpected situation. Never happened before. It happened again after that once more, but not so serious. And such an incredibly large, complex system like the space station, which went on through continuous safety control, regulation, discussion, verification, this particular detail, which was of fundamental important matter, escaped the analysis of the extremely capable engineer of NASA. So what is wrong about that? You are building this kind of beautiful infrastructure, and then something like that could stop everything, could lose astronauts because of that. This is because we are unable to build parts which are self-repairing. Everything tends to break, and we are not designing something which can repair itself. This is totally different from what nature has been developing for millions of years. From plant to animals to ourselves, everything which is alive is designed to repair itself, systematically repair itself. we are repairing our cell one by one when they're hit by cosmic rays, and the bonds are broken, or the nucleus on the cell of the DNA get damaged. There are a system to try to repair it, but we are repairing our bones, we are repairing our skin. We live, if we are lucky enough, 80 or 90 years, just because there is a continuous repair going on by design in the biological context. So let's look more carefully in what nature is suggesting us, what nature is doing. Indeed, nature has been source of many ideas. Things, for instance, the capability of flying. We started mimicking birds, and we ended up with something which is big airplane, the shuttle system, which are much more powerful than what nature can do, but which started from ideas which obviously came from nature in various cases. So let's look more in detail into that. Let's look to bio-inspiration for new technologies which may be used in space. And you will see how many surprises we can find out by doing this exercise. Self-repairing materials. We talk about self-repairing. A material, as we design those, are not self-repairing, but people are trying to develop self-repairing material. For instance, including small balls, small eggs of two-component glue, small and dispersed like a meta-material with a nanotechnological element, which once broken, because the material is breaking, also some of those elements are broken, and they, just because of random contact, tends to glue back and repair the crack. It is something very simple with respect with what our skin does when there is a damage, but the idea is the same. Bring in some chemicals which can automatically repair a break before becomes a crack, because it becomes too large. Look to this photograph. Once building and assembling a space station, people noticed that opening up the big solar panel, one of those panels were damaged, and there was a crack which was developing, and the more they were pushing to make the panel straight, more this crack was developing. It was not possible to continue like that. And you know, the panels for the space station are of essence. You cannot have a panel half closed. So to make the story short, Houston, we have a problem. And Houston said, okay, let's scratch their head. Our engineer says, you have to repair yourself. There are no alternative. It was not foreseen. Take a pin, take some wire, go that and make some sewing to repair it. And this astronaut organized an EVA connected to the Canadian arm to reach out in this extreme location on the space station, literally sewing back as it was sewing a t-shirt to repair this crack before it was getting too late. And such an intervention, which was not scheduled, was never scheduled for astronauts to get and repair the solar panel. It took, I don't know, if 8 or 10 hours of work to make just 2 or 3 points to connect and keep this crack back to shape. Nature is inspiring engineering in many, many ways. You may be surprised that the hardest material we know of comes from nature. The lymphatic teeth, the connection we keep these coats attached to the rocks are extremely hard, and they belong to these simple animals, which are considered not so important, but they have a technology to keep attached themselves to the rocks in the sea, which can stand all kinds of waves and hurricanes and extreme conditions because of the extreme strength of this material. Or if you consider the most tenacious material, which is the net the material, the wire using to create the net in the ragni, so you understand that. This material, sorry, say it again.
Spider.
Spider, thank you so much. Thank you so much. This wire at the same density is stronger than stainless steel. And look how sophisticated the connectivity of the wires one to each other in the net, which can absorb a huge amount of energy without being destroyed, stopping an insect flying at full speed without breaking, because this energy is absorbed by multiple absorber, which can dissipate the energy and keep the net intact. All of that is the technology which has been developed over millions of years by the spiders. Plenty of ideas which can be studied now with a finite element analysis. You can simulate wire by wire to understand how the net behaves and how it breaks, when it breaks. But you can also design materials made out of knots, exactly in the same way those absorbers in the net of the spider operate, which can be extremely capable to dissipate a large amount of energy. If you make enough knots per volume, you can dissipate huge amount of energy within a very small amount of material. And all of that can be studied using the technical analysis typical of mechanical engineering, only scaled down to their suitable dimensions. This is a friend that you know very well today, because it's a model of ingenuity. The helicopter which has been designed to fly on Mars. It is by no way a simple thing what JPL has achieved, because flying on Mars is extremely difficult, because the thickness of the atmosphere on Mars is very small, is of the order of 0.5% of the thickness of the pressure or the density of the atmosphere on Earth. So because of that, they had to build an helicopter which had very large, long blades, rotating very fast, 5 times faster than what it is typical for the blade of an helicopter on Earth. And they have to be extremely light, because you cannot send to Mars a lot of weight. So they have to be extremely light, long, wide, and spinning like mad. And if you take into account which is the forces which act on a rotating blade, they go with a radius to the square, distance to the square, and are proportional to the speed. Sorry, to the square of the speed, of the omega square, and they are proportional to the radius. So those materials, which have to be extremely light, are exposed to extreme tensions. So you need extremely resistant material which are light and can be shaped to keep the shape of a blade. Graphene, carbon fiber are the kind of material that can do that. They've been studied for a while and also applied in many applications. The graphene and 2D materials have on paper the capability of building the wire to create a space elevator. This concept which would allow an elevator to climb to space altitude, to orbit altitude, just using this nice counterweight system. Is an idea, is very challenging, may never be built, but on paper the graphene is the kind of material which can stand the tremendous forces which are required to allow for such a concept to be implemented. Let's discuss for a moment about micrometeorites and space debris. We know that around the Earth there are maybe a couple of thousand satellites, operating satellites, but there are more satellites which are dead, but most important, a huge amount, hundreds of thousands of fragments from the 1 centimeter of diameter up to meters, because there are also some spent stages, rocket stages, and all of that is orbiting around the Earth at hypersonic speed, typically 7 to 8 kilometers a second. One of those debris, this 1.2 centimeter aluminum debris, smashing against a 18 centimeter thick aluminum plate, it makes this kind of incredible effect. I mean, of course, this ball vanishes because it evaporates. Here is just put for reference, but it creates a shock, which is deforming the structure of this extremely thick material. So we are defending ourselves from space debris hazard, moving around the various satellites when we know that this debris is approaching, but most important, creating multiple stages of layers which are fragmenting and dissipating the energy, a similar issue to what has been discussed for the spider net, but in this case for a solid piece of material. But it would be interesting to notice that nature has advanced us tremendously from this point of view. Even the most simple stag beetle, Scarafaggio, Scarabeo, has a strength built in his skull, which is the result of a multiple layer of different material, structured and organized, exactly in the way to make it extremely resistant to shocks and to bullets which can hit his body. But look to this. This is even more surprising. There is a beetle called Bombardier beetle for the following reason. He's getting very much annoyed by ants, which are continuously disturbing himself. And the evolution has provided this beetle by capability of explode out of his body high pressure, high temperature liquid, which is basically killing the ants. So the question is, how is done? Something which has a kind of combustion chamber within his body. And if you look inside this small insect, you find out that it's the same structure characterizing multi-layer complex composite materials with a lot of connection at a given angle. Is a very light but very resistant structure designed with what we have the rediscovering today, but nature has developed this kind of technologies millions of years ago, and it has achieved a level of sophistication which we are still far away from being able to reproduce. We are very much interested in space about foldable structures, because we need large areas in many applications, but at the same time, we cannot send to space in the open configuration. So how to do that? We are learning how to expand. But look to the ladybug. If you have ever observed a ladybug, when it starts flying, it opens up its small skull, and inside that there are his wings, which are folded. They get open, perfectly open, and the ladybug can start to fly. And when she lands, these wings are retracted back and stored again inside the red-black skulls. And something like that is still outside our capabilities. We are unable, with the best technology we have, to retract and re-expand such a complex object like the ladybug, which nature has developed over millions of years. But there are many other applications which can be inspired by biology. You know what is ISRU, in situ resource utilization? in a certain sense, is getting something interesting out of nothing. When there is nothing around you and you need something, you are ingenious, sufficiently ingenious to find out how to get something useful in conditions which apparently are very, very difficult to survive. Like a desert, for instance, is it possible to get water from thin air? The Namibian beetle can do that. You know, this is a desert in Namibia. In the morning, this desert there are some winds of humid air, but it never rain. But those animals, this Namibia beetle, again a beetle, they are designed by nature in a way that when they stand against the wind, which is a humid wind, the water is condensing on their body. The water makes a drop. The drop is then drunk, and this animal can then continue their activity through the desert for the day until the next day. They get another couple of drops and they keep going. So how they can getting water from thin air is about properties of surfaces. We are able to control surface properties. This is an example of a Martian rover with their panel, the solar panels, which are made out of surface which are self-cleaning. If there is some wind, the powder, the dust goes away, and the surfaces get cleaner again, just because this dust cannot attach to the surface because of the surface properties of these panels. We have learned over the time from nature that surfaces can be hydrophilic or hydrophobic. The beetles in Namibia were hydrophilic. This lotus is hydrophobic. You cannot make a lotus wet. It's impossible because of the surface properties. We have learned how it works. We have learned from nature and also from calculation, from engineering or nanomaterials, and we have learned how to design surfaces to make them suitable for certain application, in particular having to do with water, to absorb or repel or concentrate water and things like that. And once we learned that from nature, we were able to do even different shape with different properties, metamaterials, which nature did not develop, and we can because of the technology we have. But altogether, the idea is the same. The properties of surfaces have tremendous impact on how water, air, other liquid, other gases behave when in contact with those surfaces. Or you can have the Velcro. The Velcro is a very well-known system. Everybody of us has some Velcro somewhere in his house, home, and the Velcro is coming exactly by natural design, which is used to spread seeds of certain plants. And these hooks, which are located on the seed, are able randomly attached to the fiber or the tissue of our clothes or the skin or the surface of animals passing by. And this is copied by men to apply, for instance, in space, but in many other applications, just because it's so useful and apply in many cases. It's again copied straight from nature. And let's look to things which are unable still today to do, for instance, to reproduce the technology that Gecko has, which allows Gecko to attach himself to any possible surface with a force which is well above the weight of his body. You see that is not leaving the contact because of the way his fingers are done. How does it work? the GECO technology is literally about van der Waals forces. Van der Waals forces are attractive forces which keep together molecules of different atomic systems, because they are attractive forces which act only at small distances. So you need really contacts among atoms. Nature gave to the GECO a huge quantity of very fine plumes, so to say, contact wires. You can see the scale, 1 micron is taking a few of them together, so a sub-micron element, which end with a kind of surface, which is this surface literally is being attached to a local group of atom or molecules of the material you are attaching to. And the ensemble of thousands and 100,000 of those contact points is allowing the GECO to keep the contact wherever he wants with the head down, even if it is attached to the roof. And in order to move these fingers, I mean, it's changing the angle of which those fingers are attached to the surfaces. And by changing those angles, it can remove and move the leg one by one, and attach again and continue. And these angles, by the way, are the same angle which are used by the spider to make the web anchoring. So again, nature has found over the evolution that certain angles are useful in a hierarchical level to construct extremely sturdy and resistant attach point. And this is something which also we could use in many applications using exactly the same design as nature is providing. Today we are talking a lot about 3D printing. Of course, 3D printing with respect to the standard metallurgical technologies is a huge improvement and allow us to design objects which are approaching the complexity of bones and the integration of bone and tissues and vessels in our body. Naturally, is still much better than us, but thanks to the 3D printing, we are making structures which are much more sophisticated, resistant and light than in the past. And this is something which is happening in these years, in these decades. But nature has plenty of surprises more for us. For instance, you may be surprised to find out that there are a number of living entities, plants or animals, which can survive space. Lichens, bacteria, spores, even plankton, and even animals called tardigrades, which have a dimension of 0.5 millimeter. And now you can see from this photograph, they are relatively complex. They have finger, they have a mouth, they have 6 legs. And even those animals can survive space and intense dose of radiation. Why? How it's possible? All these animals or plants have the same property. They can dry off completely or almost completely, getting in a kind of a hibernated state where water has been eliminated completely, stay in this hibernated situation for a while, even for months. We believe that also can stand years, and then come back to life when water is again available. And this has been studied in detail, and also the tardigrades in particular, they've exhibited an incredible resistance to radiation with respect to any other known animal. Why that? Which is the reason for that is because they are aliens coming from outside, from other stellar system. Probably the answer is less surprising. Probably they are just because of their what they eat and how the chemical reaction in their body are activated. They are totally different digestion system, which imply different chemistry, and as a result of that, their DNA system is more resistant than our DNA system and their cells to all kinds of radiation damages. But it's quite surprising to find out that there are animals much better designed than us to go to space for a long period, even without having sophisticated spaceships. And I will end up with this almost unbelievable natural property, the immortal jellyfish. A jellyfish is a small animal that you find also in the Mediterranean Sea. It's a small medusa. It's 4.5 millimeter size, and it prospers and lives when the water is clean and there are some food available. But this particular animal has a characteristic. When it feels that there is an issue about temperature is too high or too low, food is not enough, or there is a problem which is going to make this animal die, overnight this medusa dissolve and create back planula, which evolve in polyp, which is developed connected to the surface, the bottom surface of the sea. Eventually the polyp create immature medusa, and then the medusa grow and get back to the initial dimension. All of that without changing DNA. So the new medusa is identical genetically to the medusa which started the process of dissolution, planula, and again. So this circular system can go on and on and on for many, many iterations. In this sense, this jellyfish is immortal. And this is clearly a way that nature has developed to resist periods of radically different conditions where a medusa could not live, but where polyps or planula could survive. And this is ideal, for instance, for a very long space travel, where those jellyfish could be the one controlling the spacecraft for an extremely long period, going from Earth to Alpha Centauri without the need of caring about refreshing, redesigning completely itself. Okay, so this to give you an idea, which is in the final case very, very visionary one, of how many things we still don't know, and how many important development in technology we can be inspired by nature. There are just a few examples what I gave it to you, but there are plenty other. And you know, here I show you what is next after the solar system. The solar system extends for about 110 astronomical unit. The astronomical unit correspond to the distance of the Earth to the Sun. So 110 astronomical units. You find out what it means. It corresponds to about 14 light hours. 14 light hours is the size of our bubble. But getting across this end of this bubble, we enter the interstellar systems, and the scale is logarithmic scale. And after getting to 10 to the 3 AU, 10 to the 4 AU, with the Oort cloud, 10 to the 5 AU, eventually we reach the Alpha Centauri system. Is the closest star to us, 4.2 light year. It will take 85,000–90,000 years to get to the Alpha Centauri if you use the technology of the Voyager. The Voyager took 35 years to get outside the solar bubble. It will take 86,000 years to get to the Alpha Centauri. A little bit longer for the humankind to wait for those results, because then you have also to come back. So I will just get into this question, which I would like to present to you. You cannot spend 86,000 years getting to Alpha Centauri, to Proxima Centauri. Should we just forget about the possibility of traveling outside the solar system? Should we just forget the possibility about traveling to to close by star system with many planets, like the TRAPPIST system, where we found out the existence of 7 planets. Some of them could be similar to the Earth? Yes and no. Let me present you a concept which is really calling for a very visionary technology, but you are the person which may have some possibility to contribute to this, to solving this problem. So if you want to travel quickly through the solar system, and in particular to attempt an interstellar trip, we need a very high speed of travel, otherwise we'll never walk. How fast can we travel? In the last 100 years, we have increased about 1,000 times the speed of traveling, from 12 meters a second from the Napier racing car in the early days of last century to 17 kilometers a second, which is the speed of the Voyager spacecraft, which has exited after 35 years the bubble of the solar system. So the speed has increased by a factor 1,000, but we know that the physical limit of the speed of light is still much far away from that, because 300,000 kilometers a second versus the 17 kilometers a second is a factor close to 20,000 larger. So the question becomes to you, how can we reach this limit during the next 100 years? I want to be very generous, not this limit, just another factor of 1,000. Can we reach out of a 20,000 available factor of speed increase, just a factor of 1,000 in the next century, thanks to people like you? So propulsion of a satellite, of a rocket, can be done with chemical propulsion, which has changed a little through centuries, and the relative speed is a typical speed of a chemical reaction, of an explosion, which is a kilometer a second. It's not enough. We need much more than that. So chemistry can bring us to Mars, not to stars. If we try to figure out about solar sails, ionic engine, thermonuclear, nuclear fission, nuclear fusion, you get to the same conclusion. Don't ask me about warping space, because this technology is not yet found out, allowed or discovered. So to remain within the physics which we know of, we know that to get close to C, we need a relative speed of what we send away from the spacecraft, which is approaching C. In order to get to this incredibly high speed, relative speed, we know only 2 methods. Using antimatter, meaning transforming completely matter into energy, which is quite possible, but is extremely difficult, and directional energy, shining a powerful laser against an object. So this second technique can, to a certain extent, be implemented. So photonic propulsion could get us a factor of 1,000 or so with respect to today's capability of travel. If we take a sail and we shine through against this sail a very powerful laser, the pressure of the light can accelerate this object to a speed which, if this pressure is applied for a long amount of time, can reach a significant fraction of the speed of light. For that, people have designed an extremely tiny, light spacecraft. Of course, we're not discussing here to send astronauts to space, to Alpha Centauri. We are discussing about sending a payload to Alpha Centauri, and this payload has to be very small. So we need to take the lightest possible material, create a very thin sail. I mean, the thickness of this sail is a few atoms of thickness. I mean, everything is stretched to the limit. At the center of this sail, you attach a nano satellite, which has a weight of 1 gram and is hosting an integrated circuit which carries the fundamental memory, a small camera, whatever is needed to communicate. And then this is the concept. This experiment here, which I want to show you how the pressure of the light, this is infrared light, pushing, shining against a mirror, is making the mirror which appear on the right accelerated, running on this air cushion. You see, the light is being shined from the laser. This mirror is accelerating step by step by step. If we can continue that for several minutes, this mirror will go very quick, and the limit of this speed could be eventually the speed of light, because is the light pushing against the mirror, reflected back by the mirror, the relative velocity of c, and eventually this mechanism could increase the velocity of the object that is shining against up to reach a significant fraction of the speed of light. So laboratory application can already show that this principle is holding. However, we have to be realistic. Here we're discussing about a power of this laser light, which is comparable to the total power installed in a country like Italy. Only for a few minutes, but we're discussing about gigawatt, hundreds of gigawatts of power, laser power, to push those sails, reaching a fraction of c, 0.2 to 0.3 times the velocity of light, in order to reach the Oort cloud in 12 years, make a selfie, and send back the information from this faraway star. It is clearly a vision, it's kind of science fiction, but I can tell you the Breakthrough Starshot project, the Breakthrough Foundation is a foundation in the United States financed by a very rich entrepreneur, which has put 100 million to develop this kind of concept, is working since 10 years to developing this kind of idea, because we believe that the only way to get to the closest star is really to make a breakthrough in technology and be very free to think and to solve problems in a non-standard way, finding solutions in the same spirit that the pioneers in space race were finding every day to solve the many difficulties in sending people to space and eventually to the moon. Thank you so much.
Thank you, Roberto. It's a very exciting overview of what we can expect in the future, maybe in the far future, but I think that vision can drive the efforts of entrepreneurs and of scientists in performing their project or their business. Now we have some
Vito,
time
non ti sento. Ecco, adesso ti sento, sì, scusa, è la colpa mia.
Okay, sorry. So now we have some time for some questions, and I think that some young PhD students can find several stimulating suggestions for their research and for their studies. But just before to start, I wish to ask you a very short question about Italy. You think we are ready to sustain the progress of technology for the space in terms of investment of people, of organization? It's like in the international division of labor, Italy, it seems, can have a role, especially when we focus on specific technologies, not large program, but on specific technology. But what's your opinion about the real capability of a country like Italy to stay in this race toward the space?
Italy has a long tradition in space, as you know, which started during the space race when Generale Broglio was able to develop the San Marco project, and we launched up to 27 rockets in the 60s, the only country aside of the Soviet Union and United States to do so. So since there we had a tradition which had up and down as everything, but is maintained still nowadays. We have a series of industries from the smallest to a few large ones, which are producing satellite, rocket, in pieces of the space, a part of the space station, and we have universities and research centers. So altogether, we are a player, a real player in the context of space. How much we can push our ambitions in space, you know, is an issue which often happen for Italy, that we are very strong in certain aspects, and we are weaker on other, like to maintain a continuity and a long-term engagement on certain direction. Space requires long programs, large program investments, which are not only continuous in size, but also coherent in directions. If we don't do that and we lose the sync with what is going on at the level of the world, we may be eventually losing the opportunities which are in front of us. I always say that space is a collaborative, competitive environment. But the two things have to be together. You have to compete, yes, because there are economic arguments for the competition, but also to collaborate, because otherwise, since you cannot do everything alone, you will remain out of the circus. Okay. In this sense, for instance, ESA is extremely important because we are founder of ESA and we participate to major ESA's program, and we should not hesitate to continue to support an entity like that, even if the politics involved in ESA are more complicated, like the politics ongoing in the European Union are more complicated, only dealing with ourselves. But if we don't do that, eventually we will lose contact with the overall space evolution in Europe and in the world. We should realize that we have the knowledge, the competence, the people, the young, bright, and clever brains, and we have to work hard as everything, work hard and avoid short circuit. There are no short circuit in space. We have to find and to follow the correct way of proceeding, even when it takes longer, more effort, and more time, and even more investment, because at the end we will have developed a new generation of people, engineers, scientists, and a position in the world which is respected. Space is about being respected in what you are with your knowledge, what you are doing, and the capability of continue or develop in a certain way harmoniously what you are doing as a system, taking advantage wherever you can because it's competition, but collaborating whenever you can because it's space diplomacy, science diplomacy, and the space economy is trading, is exchanging, is working together. So it is up to us. But we have to fight against sometimes the tendency that since it's difficult to be strong in a larger, wider system, we have a tendency sometimes to come back and to look to a kind of more parochial situation. This is our main enemy, and we have to fight against that.
Okay, Roberto, thanks for the answer. Basically, I know that you have in 12 minutes lecture.
Yes,
so
again.
I please all the people that wish to ask a question. Just if you have a question very short, then I can give you room for the questions. Otherwise, I see the rector and then Professor Cupertino, and then I will give the floor to the rector. Just one question from the public. I don't know, Sergio De Gioia, are you? You have a very short question?
Yeah, just one. Thank you, Professor Battiston. Just one simple question. You've been talking about the attachment mechanism that is exhibited by gecko creature. So I think that you also said that the secret of this mechanism lies in the van der Waals forces that are acting at the atomic scale level. So I was just wondering if there are any other suggestions coming from nature that you've been discussing thus far that as the secret of a plausible implementation in the advancements of material sciences, again at the atomic scale, because I may think that probably the spider webs need for them to be created and realized artificially needs the investigations at the molecular or polymeric scale level, but not lower than that, or folding structures that again you have been discussing need investigation at even higher scale than molecular scale level. So what application in addition to the gecko-like attachment mechanism must be instead investigated at the atomic level? Thank
you for this excellent question. As you may see from my slide, I'm very fascinated about the power of nature, and I give you an example which always fascinated me a lot. Chlorophyll synthesis. Everything around us is green. All plants are green, basically. Forget about some exception. Everything is green. And because the chlorophyll process is built around certain molecules, very complex molecules, a sequence of molecules, which are, at the end of the day, creating this green effect everywhere. Different greens, but okay, always green. And if you look into that, these are based on chemistry, but more than that, on quantum coherent effect, which we don't understand fully even today, after a century of researchers and maybe 12 or 15 Nobel Prizes awarded on this topic. And the chlorophyll is everywhere, in every plant, in every seed, everywhere, and we still are fighting to understand it. Can you imagine if we could make solar panels which are similar to leaves? They can be, clearly, neutral from the point of view of pollution and things like that, cheap and easy. Okay, that would be a revolution, and it's too difficult for us. So understand quantum physics and atomic physics for solar energy extraction is an example of that.
Thank you.
Well, last question, a few seconds, Professor Cinefra.
Good afternoon.
Yes.
So I have just a question about metamaterials, because I'm working on that, but for different kind of applications, but different from that one that you mentioned in your presentation. But I'd like to know more about your application, the application that you mentioned in your presentation. Thank you.
The main application which I mentioned was about the behavior of those materials with respect to water. Drops of water, when they are on the surface of such material, can keep their spherical size without attaching to them, so they are repellent. So very simple push will take this water away, or they can adhere with a more or less extension. They can get more or less wide on this surface, and depending on that, you can obtain several effects. And these also apply to dust, as you can have seen in those panels on Mars. And applications are many. And once you understand that, when the engineer or physicist understand the details of those properties, you can design a code linked to application. The one which I underlined are about the water interacting with surfaces, but there are many other applications possible And I'm not an expert in this field, so I just got this as a very curious topics that is very wide in many directions.
Yes, I have to say that this is new for me because I'm working on acoustic metamaterial. So in that case, the objective is to capture acoustic waves. That is completely different.
Okay.
Okay, thank you. Thank you.
Okay, so Roberto, thanks again. Just a few words for the conclusion to the rector, and I hope to see you next time in Bari at Politecnico of Bari.
In presence.
Roberto. Please, Francesco.
Thank you, Vito. I'm here just for a final thank you to Roberto Battiston. Thank you, Roberto, for your availability, your kindness, your friendship. When we started thinking about the cycle of seminars, such inspiring speeches in the area of aerospace, you were one of the first I thought of as a speaker, because if I have to think about somebody that could be inspiring for our PhD students, based on your experience, based on your ideas, it's you, Roberto. And the few minutes I managed to follow of your final at the end of your seminar convinced me that I was right. This is a complex area. Aerospace is wide as much as space, maybe, you know. And the idea of this cycle of seminar is to show to our students, to the community of Politecnico di Bari, to our region, the complexity of the aerospace sector, but also the complexity of possibilities that are offered to us in order to improve our research activities, improve our relations with the public and private companies in our region, but also outside the region of Puglia. So I do not want to add anything else. Thank you again. I think this is one of the milestones of our route towards the establishment of the area of the aerospace engineering and science at Politecnico di Bari with this new PhD project. I hope to see you soon. I hope in person, Roberto. I hope that the conditions soon will be better for all of us, and we can start again to meet each other, to talk, to exchange ideas about and not only about aerospace. Thank you.
Thank you, Francesco, for those words, and I thank you, Vito, and the best wishes for the continuation of this school, very important school. Thank you. Ciao.
Thank you.
Ciao.